Hello everyone. Assalamualaikum and a very good morning. I be to Dr. Haslina and also my fellow friends. So today our group are going to present about P block element, which specifically for group 13 boron element. My name is Shasha and I will be the first presenter. I'll be explaining about simple hydrides of boron and also metal borides. Followed by Akila, who will be explaining about boron trihalides and also boron oxygen compound. Proceed with Amirin, who will be explaining about compounds of boron and nitrogen. Last but not least, we have Hani, who will be explaining about higher boron and also borohydride. Okay, first of all, what is boron hydrides? Boron hydrides is the binary compound of boron with hydrogen. These hydrides of boron are also known as boron, and it can be divided into several series, which is arachnoboron and also nidoboron. But the simplest hydrides of boron is known as diboron with a general formula of B2H6. Okay, so basically there is 3 ways in preparing diboron. First, by a reduction of boron trifluoride etherate with lithium aluminium hydrides in diethyl ether. Next, by the oxidation of sodium borohydride with iodine in diglam as solvent. So basically the second way is usually we prepare diboron in the laboratory, and the third one is by the reduction of boron trifluoride with sodium hydride. So the third way is usually we use to prepare diboron in the industrial scale. Let's move on to the uses and application of diboron. Diboron is one of the chemical substances that has many numbers of application in various fields, of which diboron is used as a rocket propellant, and it is utilized in the manufacture of borophosphosilicate, which is a form of glass. In most of the chemical reaction, diboron employed as a reducing agent. Diboron also is used as a catalyst and rubber vulcanizer in the polymerization reaction, and it is even used as a doping agent in the manufacturing of semiconductor devices. Okay, next we proceed to physical properties of diboron. Diboron is said to be a colorless and highly flammable type of gas at a room temperature, and at the high concentration, it ignites rapidly in the presence of moist air. Diboron also has sweet smells and has a boiling point of about 180 Kelvin. Diboron also mixes well with air and easily form explosive mixture. And last but not least, long-term exposure to low concentration or short-term exposure to high concentration of diboron can result in adverse health effects from inhalation. Okay, now let's see the chemical properties of diboron. First, we can say that pure diboron does not react with air or oxygen at a room temperature. However, an impure form of diboron does, and it will produces boron trioxide. Next, diboron can react with methyl alcohol to give trimethyl borates. The third one, the reaction of diborate with methyl hydrides will produces a methyl borohydrides. And the fourth one, diboron also can react with ammonia, and at a low temperature it will produces ammonia boron, but in a higher temperature it will produce a borazine. Okay, last but not least, diboron also take place in the hydroboration of alkene and aldoboration of alkenes.
A very good morning to Dr. Haslina and to all of my course mates. Today I will be presenting about boron trihalides and boron oxygen compounds. So let's get into boron trihalides first. So what are boron trihalides? Boron trihalides is a compound that consists of boron and halogen elements, which are fluorine, chlorine, iodine, and even bromine. So they are trigonal planar molecules. They are sp2 hybridized, and the angle between the molecule is 120 degrees. So the properties of boron trihalides: BF3 and BCl3 are in gaseous form, BPR3 is in liquid form, Bi3 is in solid form. So boron trihalides are electron deficient. Why we say that? So as an example, we choose BF3. So in BF3, boron has only 3 electrons to share with 3 fluorines. So after sharing electrons with fluorines, boron has only to settle down with only 6 electrons. That means boron doesn't achieve its octet rule. So in order for boron to achieve its octet, it has to gain 2 more electrons. From where? From Lewis space. Boron trihalides act as Lewis acid. So that is the sequence for the Lewis acidity. So we can conclude that Bi3 is the strongest Lewis acid. The order of relative acid strength is contrary to that expected based on the electronegativity and atomic size of the halogen atom. That means the sequence of Lewis acidity is not depending on the electronegativity and atomic size of halogen atoms. So as you can see in the diagram, in BF3, boron has empty 2p orbital and the lone pair of electrons in 2p orbital of fluorine can be easily donated and overlap with empty 2p orbital of boron. So you can see that in BF3 it only involves 2p orbitals compared to BBr3 and Bi3. It involves 4p 2p and 5p 2p respectively. So we can see that in BF3, the donation of electron from fluorine to boron is more effective. Why? Bi3 is still the strongest Lewis acid. Go back to the concept of Lewis acid that I have stated in the first slide. Lewis acid is a compound that is electron deficient. So which of these 3 compounds is most electron deficient? Bi3, because the donation of electron from iodine to boron is less elective, and that is the reason why Bi3 is the strongest Lewis acid. And most electron deficient, Bi3. Melting and boiling points of boron trihalides increases from BF3 to Bi3. This is due to the increasing in atomic mass and van der Waals force. Reactions of boron trihalides compounds. All the boron trihalides form simple Lewis complexes with suitable bases. So in this example, BF3 will react with ammonia. It will form F3b and H3. Next, all the boron trihalides undergoes hydrolysis to give boric acid. Synthesis of boron trihalides. Preparation of BF3. The reaction of B2O3 with CaF2 in H2SO4. This reaction is driven in part by production of HF from the reaction of H2SO4 with CaF2 and the stability of CaSO4. So that means H2SO4 readily reacts with oxides and affinity of boron for fluorine drive reaction forward. So next, BCl3 and BBr3 can be repaired by direct halogenation of oxide in the presence of C. These are the uses of boron trihalides. Boron trifluoride act as a catalyst in petrochemical industry. Next, boron trichloride is used in the refining of aluminium, magnesium, zinc and copper alloys to remove nitrides, carbides and oxides from molten metal. Let's get into boron oxygen compounds. Boron forms boric acid, B2O3 polyborates and borosilicate glasses. Boric acid with formula BOH3 is a weak proton donor in the sense of Bronsted acid, but it is a Lewis acid. It can accept an electron pair. Boric acid does not dissociate in aqueous solution, but it is still acidic due to its interaction with water molecules. It is acidic due to its reaction with OH- from water and forming tetrahydroxy borate complex. Next, synthesis of boron oxygen compounds. Simple borate esters can be prepared by the reaction of boric acid with an alcohol in the presence of sulfuric acid, which are compounds of the form BOR3. Next, boron oxide, BO, is acidic and is prepared by dehydration of boric acid. Next, the rapid of molten B2O3 or metal borates often leads to the formation of borate classes. The fusion of sodium borate with silica leads to the formation of borosilicate classes, such as the example on the left side. These are the uses of boron oxygen compounds. Borates are used as a bleach in laundry powders, automatic dishwasher powders, and whitening toothpaste, such as sodium perborate. Second, boric acid is used as antiseptic, eye lotions, and food preservative.
So I will continue to explain about compound of boron with nitrogen. So the simplest compound for boron nitrogen is boron nitride with formula Bn. This is how we synthesis, or the synthesis process for boron nitride. So boron nitride is easily synthesized by heating boron oxide with a nitrogen compound. So here we heat boron nitride with ammonia, which is, it contains nitrogen compound in it, and we get boron nitride and H2O, and we must heat it up to 1200 degrees Celsius. So this is a picture of layered boron nitride structure. Boron nitride can exist in various crystalline form. So here is one of the form, which is a layered boron nitride. It consists of planar sheets of atom like those in graphite, and also have similar physical properties like graphite. It is very similar like graphite, but it also have a different. So I will talk about in the next slide. So this is the properties and application of boron nitride. Boron nitride properties, and it is whitish in color, or we call it white graphite because it just look very familiar and similar to graphite. It is extremely hard in a cubical form or cubical structure. Like I said earlier, it has various crystalline form. So this is the second form of boron nitride, and it is the second hardest material behind diamond. So it is also slippery. It is an electrical insulator, which means it can't conduct any electricity, and it is thermal insulator, which is it also can absorb or take any heat, and low thermal expansion. So this is the application for boron nitride. It is used in aerospace industry because of the thermal expansion and low thermal expansion and thermal insulator. Also, with that factor also, it can be used as high temperature cubicles, and because boron nitride, the layered boron nitride is slippery, so it can also be used as lubricant. And also boron nitride can be found in cosmetic and self-care product, as it is a non-toxic and no known hazard in the contains in boron nitride. So it can be added up to 10% of the cosmetic product. For example, there is lipstick, nail polish, and foundation. So this is the other compound of boron nitrogen compounds. First, amine borane. So this is how we synthesize amine borane, and amine borane is isoelectronic with hydrocarbon, means that it have the same valence electron with hydrocarbon. Second one is aminoborane. This synthesis of aminoborane. And aminoberane is isoelectronic with ethene and transit existent in the gas phase only. And this is borenzene. So this is the process of synthesis for borenzene. And borenzene is isoelectronic and isostructural with benzene.
Okay, what is metaborite? Metaborite is a binary compound that consists of boron and a less electronegative metal elements. For example, silicon borate. Metaborite can be divided into two groups, which is boron-rich borates and also metal-rich borates, with the general formula of M and Bm, which is M stand for metal and B stand for boron. Let's proceed to the physical properties of metaborates. Metaborite is extremely hard and it is as hard as diamond. Metaborite is also a non-volatile substance and have a high melting point, which is 3000 degrees Celsius, and is a decent electrical conductivity. Okay, next we proceed to the preparation of metaborites. Metaborites can be prepared by heating metal with boron in 1100 degrees Celsius, and we can also prepare metaborites by heating the metal oxide with a mixture of diboron trioxide and carbon in 1500 degrees Celsius. And last but not least, we can also prepare metaborite by heating the metal with a mixture of diboron trioxide and boron carbide in 2000 degrees Celsius. Lastly, about the uses and application of metaborites. Magnesium diborite are widely used as a superconductor at 39 Kelvin and also used in MRI, whereas titanium diborite, zirconium diborite, and chromium diborite are used in a turbine blades, combustion chamber liners, and also rocket nozzle. Lastly, beryllium borides are widely used as a bulletproof protective clothing and protective armor of aircraft.
Assalamualaikum warahmatullahi wabarakatuh. So next, me Azlihani will introduce about higher boron and borohydrides. So first of all, borons are compound consisting of boron and hydrogen. They were investigated systematically by the German scientist Alfred Stock at the beginning of 19th century. The most basic example of diboron is B2H6, and all borons are electron deficient compounds. For B2H6, usually 14 electrons are needed to form 2C, 2E bonds, but only 12 valence electrons are present. Because of this, there are 2 BHB bonds like the picture, which have 3 centers but only 2 electrons. This can be interpreted as a molecular orbital that is formed by combining the contributed atomic orbital of the 3 atoms. In more complicated borons, not only BHB bonds but also BBB occur. In such a bond, 3 p atoms lie at the corner of an equilateral triangle with their sp3 hybrid orbital overlapping at its center, as the picture. One of the common properties of boron is that they are flammable or react spontaneously with air. They burn with a characteristic green flame, and they are colorless diamagnetic substance. So next, it's about Wade's rule. Wade's rule help to predict the general shape of a boron from its formula using correlation between the number of electrons, using the number of boron atom. As the table shows, they have 3 main structure, which is closo, nido, and arachno. So from the example shows, the 3 main structure is the main, but they have one more, hypoboron, but it's not the important one. These the 3 main that I'll explain, which is related by successive removal of a BH fragment and addition of H or electron. So first of all is closoborons. It's close deltahedral without BHB 3C2E bonds, thermally stable and moderately reactive. Example is B5H5. The ion builds up a trigonal bipyramidal polyhedron like the picture. And next is nidoboron, which is closoboron with one corner less, an addition of 2 hydrogen atoms instead. It's BHB bonds and BB bonds are possible. Thermal stability lies between closo and arachnoborons, and for example is like B5H9, its structure can be assumed as the octahedral deltahedron with a one-corner tetragonal pyramid. And the last one is arachnoborane, which is it is closoborane deltahedron but with 2 BH units removed and 2 H atoms added. It has to have BHB3C2E bonds, thermally unstable at room temperature and highly reactive. As for example, the structure can be derived from B6H6 deltahedron with 2 cornerless. Synthesize higher boranes and borohydride. The reaction has to be done under vacuum or with exclusion of air because diborane burns in contact with air. This is the synthesis for borane, but for higher boranes are obtained by controlled pyrolysis of diborane in the case phase. Like pyrolysis followed by rapid quenching provides one method of converting small borane to larger, as pyrolysis is a process of chemically decomposing organic matter from small to larger one. So for mechanism formation, tetraborane, for example, it's like that. Like B2H6 to BH3 plus BH3. For this synthesize, it's difficult because of highly unstable because of arachno. So to improve it, we immerse it from hot reactor and quench it cold surface. It's more stable if it was needle. So next is characteristic reaction of borane and borohydride. So first, we can cleavage of BH2 groups from diborane and tetraborane by NH3. Second, we can deprotonation of large boron hydride by bases. And for the next is we can reaction of borohydride with borohydride ion to produce larger borohydride and ion. Like the example below with polyether, it was the reaction of boron hydride with borohydride ion to produce the larger borohydride is like that. Like this one. So that's all from me. Thank you.
Example, it contains 20 milliliters of boron tribromide. This yellowish liquid smokes in the air very actively, forming fog from hydrogen bromide. Reacting with water forms a significant amount of gaseous hydrogen bromide. Concentrated sulfuric acid oxidizes boron tribromide to bromine element. These dark red particles got there from the cap that kept the bottle with the reagent closed. The resulting transparent glassy mass consists mainly of boric acid, and the emitting gas bubbles are sulfur dioxide.